So when you do this assignment, one of the things I just want to add is I think I'm going to start placing the review questions on the homeworks so that you can find them during test time, or if you just wanted to, just see some additional examples. So just be aware of that, but I will talk about this assignment now. So the first part of it, you really need to just get from your notes. I'm looking for very specific things like opposite H, exactly K, and then tell me in your own words, what do these do? And show me that you know the parent function points and graphs, okay? So down here, all you're doing is taking the parent function, you're drawing it, -2, 2, -1, 1, 0, 0, 1, 2, and 2, 2, and you're placing it at that point. Now, if you would alternately rather think about this as a translation, now that you know what that is, you could think about this as left 1, up 1, and take your parent function points and go left 1, up 1. Take this point, left 1, up 1, left 1. Sorry, left 2, up 1, left 2, up 1. Same thing with this. You take your parent function, you go left 1, up 2. So you would just do it for each point. So how do you do the function? You write down the absolute value, and you put this in as opposite H, and you put this in as exactly K, just like at the top of the paper. And you do that for each of them. Opposite H, exactly K. Opposite H, there is no K, so I put nothing down. And so on all the way through. Just don't forget that when you draw the greatest integer function, it's so tempting to draw a line, but students, it is not a line, it is a bunch of barbells. So draw your dots, move them if you want, right 3, down 2, each point, right 3, down 2, right 3, down 2, right 3, down 2, and then draw your barbells. So when I come to the back, you're kind of doing that exactly the same thing, but you have to tell me the vertex. So opposite H, -3, exactly K, 2. Draw your parent function of the absolute value, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, and then go left 3, up 2 for all the dots. Left 3 up 2, left 3 up 2, left 3 up 2, which gives you your vertex. Left 3 up 2, left 3 up 2, there's your graph. Describe what happened. I went left 3 up 2, and I had no reflection. So now that you understand the basic, let's talk about when it gets complicated. So the first thing you see in this problem right here is you're probably looking at it and saying, that's a -1. Why'd you say that is -1? It's supposed to be opposite H. The problem is that this negative has to be factored out as a GCF, and GCFs are critically important in the entire course. So you're actually going to want to take that -1 out and make this part, sorry, the graph's actually in the way there. So if you take a negative away from a -1, you get +1. So divide the negative here and you get X, divide the -1 here, you get 1, and then actually graph that. You would want to then scratch this out and not look at it. So you start with your parent function, which is, I will redo this entire problem, give me 1 second. So you start by doing the parent function of the quadratic, which is -2 squared is 4, -1 squared is 1, 0, 0, 1, 1, 2, 4. The next thing you do is you do this, and what's actually happening mathematically is you're taking values on the x-axis, like -2, -1, 0, 1, and 2, and you are actually dividing them by -1. That's what's happening to all these numbers. So if you take -2 and you divide it by -1, you actually get +2. And so this dot has now been reflected to here because -2 divided by -1 is 2, and it's telling you to graph that point here. The height didn't change, it's still 4, but the negative became a positive. Same thing here. 0 doesn't change, the 1 becomes -1, and the 2 becomes -2. So essentially this point went over here, and this point went over here, and these points went that way. That's the reflection over the y-axis. Once you do that, you can graph this vertex point if you want. If you want to go to -1, 2 and put a dot there and then graph everything from there, you can. Alternately, some students will go, I'm going to move every point left 1 up 2. So if I come in here and go left 1 up 2, 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 that is my graph. So it's not that bad. There's actually a really cool way to check it too. Pick any point you want. Why don't we pick this point? This point is -1, 3, and graph it. Plug it back into the original problem and see if it's graphed accurately. So if I put -1 here, negative times negative is 1. 1 minus 1 is 0. 0 squared is 0. Then you get 2. So let's see. Did I make a boo-boo there? So negative. Oh, I wrote it down wrong. My apologies. So make sure you write the point down correctly. I'm kind of glad that that happened in the video. So when you check, make sure you actually accurately describe that point, negative 2, 3. So negative 2 right here would become positive 2. 2 minus 1 is 1. 1 squared is 1. 1 plus 2 is 3. So you can easily check it. Just make sure you know what you're doing. You're taking your time and you accurately pick a point. If one point doesn't work, let's use 0. If I put 0 under there, right, I get 1. 1 squared is 1. 1 plus 2 is 3. Pick a second point if you need to. All right, so what's going on with this one? Because this is also a reflection, right? Very important thing to understand. I mean, really, this is super important. If you have an exponent problem, like a cube or a square, if you do not have a parentheses, you do not have a B or an H, which means this is a cube with no parentheses. That means that this thing is an A. This is a cube with no parentheses. That means this thing is a K. So important to understand that, or else you'll think this is a B, you'll think this is an H. You can't have an H or a B without a parentheses. When you graph cubes, please make sure you go by twos, as you see me doing. Negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0, 0, 1, 1, 2, 8. We now do the reflection. Remember what you're actually doing here is you're multiplying negative 8 by negative 1, right? You're taking this negative 1 and you are multiplying times negative 8. So what that's going to do is this negative 8 will now be at positive 8. This negative 1 will now be at, so negative 8 is at positive 8. Negative 1 is at positive 1. 0 does not move until translation step. This will be at negative 1 and this will be at negative 8. So that's the reflection over the x-axis. And now you can, if you want, you can go to 0, negative 2 and move the graph, or you can say, hey, this is really saying move everything down 2. So you could just do that point by point. Down 2, down 2, down 2, down 2, down 2. Draw your graph to show Mr. King that you want me to grade those dots right there. Please don't forget to then tell me what happened in this section. So the rest of it's pretty self-explanatory. It probably would be a good idea for me to go over a greatest integer function, otherwise known as the floor. So in this problem, there's nothing weird in terms of DCFs. There is on number 19, so make sure you DCF it and you'll get that graph. But on number 17, what happens is that we graph the greatest integer function, which looks like a line, but it's actually barbells, right? Those are actually little barbells. Okay, so step 1 is done. Step 2 is to multiply the outputs by negative 1, which will reflect them over the x-axis. That will not change the open closedness. Like this is still going to be a barbell here at closed open. This will still be here. It'll still be closed open, closed open, closed open, closed open. And they went, again, negative 1 times negative is positive, and the positive ones become negative. So now we have the translation, which makes this positive 2 and negative 1. Remember, opposite H exactly K. This is going to move right. This is going to move down. So let's just do that to every point. All right, so right 2, down 1, 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 and those are now barbells. Please don't accidentally make that a graph of a line. Okay, so this is great, but I've made my domain limited. Notice that this domain is all real numbers. So you do need to come back, and I'll just draw it in orange or something, and fill in some additional sort of extra points to show people that you understand that the greatest integer function has a domain of all real numbers, negative infinity to infinity. The range is all integers. That is how you would describe that. Mathematically, we maybe don't know how to do that yet, but the domain is negative infinity to infinity. So at the bottom, the question is, how do I make an equation from a graph? Same way, right? Math is the same thing, only different. I start with the parent function. Here's my parent function. Mathematically, that means I have the absolute value. Okay, always put an X right there. Do I see a reflection? No, that means I do not put anything here. Do I have a vertex? I do. My vertex is right here. I label it, right? That vertex is 1, 2. be careful with labeling your points. I mean, it's just super easy to mess that part up and then you get frustrated. So H is here and K is here. H is opposite, -1. K is exactly the same. Your domain from the first chapter, beep, -infinity to infinity. The range from the first chapter, nothing, 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 beep. You started at 2. It has a solid dot. It goes to infinity. And then you just continue that process. Please notice that this one is a quadratic and it's reflected over the x-axis, so you'll want to put a -1 there. Then you do your opposite HK, the range,